Hello there, and today we have a nice integral we're going to be complex analysising, which should be fun, and that is the integral from 0 to 2 pi of cosine to the 2n of x dx. The reason it's 2n and not just normal n is because for any for any odd integer in the exponent, like close to the third, the integral by symmetry will just be 0. So to make things slightly more interesting and to actually get a result that's not trivial or 0, we're going to be using 2n, where n is just an integer. So to actually get started, enough talk, what I'm going to do is just express cosine as just in terms of e to the x. So we have cos of x equals e to the xi plus e to the minus xi over 2. And I'm just going to sub that in real quick. So we're going to have the integral from 0 to 2 pi of e to the xi plus e to the minus xi. And then that's going to be to the 2n power dx. And then I'm just going to put the 2n to the negative 2n just on the outside just to simplify things. We'll come back to that at the end. And now I'm just going to do a quick use of u equals e to the xi. And what this is going to do is allow us to integrate over the unit circle in the complex plane and apply the residue theorem, just to find our one residue in the center. And yeah, that'll be our answer actually, or 2 pi times that. But yes, so to actually do that, we do need to do this use up. So u equals e to the xi, meaning that du is equal to iu du. And just to sub that in real quick, we're going to have still 2 to negative 2n integral over c this time. It's so fun to write that. U plus 1 over u to the 2n. And then divided by iu du. And I'm just going to simplify the integrand a tiny bit more just so that we can kind of take advantage of the residue theorem. So I'm just going to multiply top and bottom by u to the 2n, meaning that our integrand is just going to become u squared plus 1 to the 2n divided by u to the 2n plus 1. And I'm just going to throw the I out into the, throw the I out of the integral. It's just going to make things a little bit simpler. So we're going to have negative I 2 to the negative 2n integral over c still of u squared plus 1 to the 2n all over u to the 2n plus 1 du. And just to get a sense of how we're going to evaluate this, I'm just going to write out the residue theorem real quick. So the residues of some function x at, say, I'll specify at 0, I suppose. This is just going to be equal to the limit as, in our case, u goes to 0 of 1 over gamma of whatever the degree of our pole is. Whatever the well, technically this should not be gamma, it should be the factorial, but they're one and the same. So it's going to be the degree of our pole subtracted by 1, so in this case it's just going to be 2n plus 1 factorial, which is just gamma of 2n. And then, actually no, that should be 2n factorial. I'm very sorry. Whoopsie. I've been doing too much gamma function stuff. Okay, so 1 over 2n factorial. And then we're just going to have the same thing, but sort of for the derivative. So we're going to take the degree of our pole and differentiate it that many times minus 1. So we're going to have the 2nth derivative, that's a mouthful, of u to the 2n plus 1 over u to the 2n plus 1. Those cancel, so we're just left with u squared plus 1 all to the 2n. And these are just our residues, and just by the residue theorem, 2 pi I times the residues is just going to be the value of our contour integral. So I'm just gonna save the 2 pi for the end because it's not too relevant as of the moment. The most pressing thing right now is really just this limit and derivative. So what we have here is the limit as u goes to 0 of d over du to 2n, and then a u squared plus 1 plus 1 to the 2n. So what we have here is a little bit weird because we're taking the nth derivative in a way, but what I'm going to do is expand this as using the binomial theorem. And in this way it'll be a lot easier to see how all of our terms are actually going to go to 0 except for 1, which is pretty cool. So just expressing this in terms of the binomial theorem, this just gives us from k equals 0 to 2n, 2n choose k, times u to the 2k. And now we need to differentiate this. We need to differentiate this to 2n times, meaning, so let's actually kind of think about what this means. So for our upper bound here actually is going to be 4n, because for the absolute maximum, so if we plug in 2n for k, we're going to get 4n. So 2k must be less than that, but it also must be, greater than 0. So let's kind of think about when we differentiate this. For 2k being less than 2n, the only thing we're going to be left with is 0, and that's because we're differentiating it 2n times. So say we have like, say we have, well, I'll just use that as an example. If we take like the fourth derivative of say like x to the third, that's just going to be 0 because the degree of the derivative is greater than the degree of the exponent right there. So using that same logic, really, for 2k being less than 2n, well, we're just going to get 0. But one thing that we do have to remember about is this limit right here. So the limit as u goes to 0, meaning that any term that has a u in it is also going to 0. Basically meaning that the only term that's not going to go to 0 is going to be when 2k is equal to 2n or n equals k. And because of that, we can just take our binomial formula right here. And what we can do is really just, what we can do is just throw in k equals n and drop the summation. So let's do that. We actually drop the summation and the limit, actually. So we're going to have still the second, well, the 2nth derivative of du to the 2n, or the 2nth derivative, yeah, of 2n choose n times u to the 2n. And now what we have here is just, we have the 2nth derivative of u to the 2n, which is, well, you differentiate u to the 2n times, you're really just going to end up with 2n factorial. And we're going to have, don't forget about our 2n, choose n term here. And this is what we're left with when we calculate our residues. So I'm going to kind of combine everything that we kind of collected, if that makes sense. So what we're left with here is we have 2 pi I times our terms out front here, so negative I times 2 to the minus 2n. But then also times 1 over 2n factorial from our residue theorem times 2n factorial times 2n choose n. And this looks really messy on the surface, but really a ton of this cancels because the 2n's factorial cancel. The I and the negative I cancel because I times negative I is just 1. So the only thing we're left with really is 2 pi over 2 to the 2n times 2n, choose n. And this right here is actually just our answer. We can also express this in terms of factorials if you really want to. So you could say actually that this is pi divided by 2n plus 1, or 2n minus 1 actually, times 2n factorial divided by n factorial squared. This is another way you could express it. Both are the same, but depending on which one you like, they're both kind of cool. So anyway, I hope y'all enjoyed this little video, and yeah, catch you in the next one. Thank you for watching.